So let's work through some examples in 4.4. Hopefully you've watched the video that goes along with this section. So now let's try to do a few homework problems. So let's do this one. Let's evaluate the integral that goes from 0 to 1 of x minus the square root of x over 3 dx. So let's evaluate this definite integral, or this Riemann sum. And instead of having to do it the long way, and if you watch the video, then you should have learned the fundamental theorem of calculus that says in order to evaluate this definite integral, we can find the antiderivative of the function, and I'm going to just call that big F, and we can evaluate it at the left endpoint and the right endpoint and subtract the difference. So find the antiderivative, evaluate it at 1, evaluate it at 0, and subtract those. So one question we have to ask ourselves is, how do we find the antiderivative for this function? 3 on bottom is equivalent to having a 1/3 times that fraction. That's a coefficient, so we can put the 1/3 in the front. Also, we have 2 terms, so we can get their antiderivative separately. And since we have a square root, we need to change that to x to the 1/2 power. Now, in order to get the antiderivative of each term, these are simply power rules. This is x to the first, this is x to the 1/2. So the power rule says we do x to the 1 bigger power over that power. So 1 more than 1 is 2 over 2. If we do the 1 bigger power here, 1 more than 1/2 is 3/2 over 3/2. Or instead of dividing by 3/2, we can multiply that times 2/3. That's our antiderivative. We don't have to include a plus c at the end, because imagine that we did. Let's put one in just for kicks right now. And we're evaluating this from 0 to 1. So the way this would work is we would have a 1/3 in front, and we would put a 1 everywhere we have an x, because x is our variable of integration. So we would have 1 squared over 2 minus 2/3 times 1 to the 3/2 power, minus, do the same thing and put a 0 in. So 0 squared over 2 is 0. 0 to any power is 0, times minus 2/3 is 0. And I didn't put here's my plus c here, here's my plus c here. So we're going to have a 1/3 c here, and we're going to subtract a 1/3 c. So those are just going to cancel out anyway. So when we evaluate a definite integral using the fundamental theorem of calculus, we don't have to include the plus c, because when we plug those numbers in, they're going to go away. So we have a 0 minus 0, so that whole thing is gone when we evaluate it at 0. So we just need to simplify this one. So we have a 1/3 out front. 1 squared is 1 over 2, so that's 1/2. Here, 1 to any power is still 1 times 2/3. So now we can either distribute and then get like term, or get a common denominator, or we can put these together and then multiply by 1/3. So our common denominator will be a 6. So if we change this to having a 6 on bottom, we'd multiply top and bottom by 3, so that's 3 over 6. Multiply here and here by 2, so that's 4 over 6. So we have 1/3 times negative 1 over 6. 1 times negative 1 over 3 times 6. And that's what we get when we evaluate that definite integral. Now let's do one that has some trig in it. So let's evaluate the definite integral from 0 to pi of sine of x minus 2 dx. So again, the fundamental theorem of calculus says to get the antiderivative of that function, and then plug in pi, plug in 0, and subtract them. So the derivative of sine is cosine. The derivative of sine is minus cosine. When we integrate a constant, we pick up our variable. And remember, we don't have to have the plus c. So when we plug in a pi, we have minus cosine of pi minus 2 times pi minus plug in a 0. So minus cosine of 0 minus 2 times 0. And with regular functions, polynomials, things like that, when we plug a 0 in, usually the whole function goes away, or the whole antiderivative goes away. But that's not always true, especially with trig functions. Cosine of pi is -1. So we have minus the -1, which is a positive 1, minus 2 pi. Cosine of 0 is 1, so minus 1, and that part is 0. So we have 1 minus 2 pi minus a -1. Well, minus a negative will make that a plus 1. So if we combine like terms, we have 2 minus 2 pi. And that's what we get when we evaluate that definite integral. So let's do this one. Let's suppose that we want to find the area of a certain region. And let's suppose that region is given by the function y equals 1 over x squared on the interval from 0 to 1. Not 0 to 1, from 1 to 2. So if we sketch our function, when x is 1, 1 over 1 is 1. When x is 2, we have a 2 squared on bottom, which is 4, so 1/4. So our function is doing like that. And the area we're wanting to look for is the area between this curve and the x-axis. So this shaded region here. So if we were to go through the whole Riemann sum, it would be the sum of the y value, which is given by our function, times the width. But when we convert that to a definite integral, our y value is given by our function. Instead of having delta x, we have dx. And our interval from left to right goes from 1 to 2. So our function, 1 over x squared, again, delta x becomes dx, and we're going from 1 to 2. So that will give us the area between our curve and the x-axis. So we're not going to do it the long way anymore. We're just going to use the fundamental theorem of calculus. So we need the antiderivative of that. We don't really have a quotient rule, so rewrite that as x to the -2. And that we can do. That's just the power rule, x to a power. So that's x to the 1 bigger power over that power, and we're evaluating that from 1 to 2. So before we plug in, let's simplify our function. We can put the negative out front. Instead of calling this x to the -1, we can call that 1 over x. And we want to evaluate that function from 1 to 2. So if we put a 2 in, we have -1 over 2. Put in a 1, we have a -1 over 1. If we simplify that, we get a -1/2 out front, minus a negative makes a positive. 1 over 1 is 1. And 1 minus 1/2, of course, is just 1/2. So that's all we have to do there. So that's much easier than having to break our interval up into rectangles, find the area of each rectangle, and then let the number of rectangles go to infinity. So that's great. The only issue is our function has to be some function that we know how to get the antiderivative. If this is a function that we're not able to integrate to get the antiderivative, then we're not able to use this method. But for a while, the functions that we're going to be given are things that we can either integrate directly, or we can do some algebra to rewrite them and integrate them. So let's look at one or two more questions. Let's begin with this one. One of them says, find the area of the curve bounded between y equals negative x squared plus 16 and y equals 0. So first of all, let's look to see what that looks like. For y equals negative x squared plus 16, when x is 0, we're at 16. And this is an upside down parabola that does this. Y equals 0 is the x-axis. So it wants this area here. So we need to find out where they intersect. This one is going to be hopefully easy enough to figure out, but if we had a harder function, in order to find our interval, we need to know these points of intersection where the horizontal line intersects that particular curve or that parabola. So they intersect where the two are equal. So where minus x squared plus 16 equals 0. If we add x squared to both sides, we get 16 equals x squared. If we take the square root of both sides, we get that x is plus or minus 4. So that's our interval, from negative 4 to positive 4. So in order to evaluate that, we put our function in times dx, and our lower limit is negative 4, our upper limit is 4. And then we just take the antiderivative, we plug in the top number, we plug in the bottom number, and we subtract. So for this one, I'm going to leave that to you as an exercise. The other thing I want us to do is to look at calculating an average value. So average value is actually something that's kind of useful. And one example that we've done, or that I've dealt with in the past, is for flying model rockets. If you've ever built model rockets, these Estes model rockets, they have an engine that goes in the back. And that engine has some powder in it that when you ignite it, it accelerates the rocket up into the air. And we actually have a sensor down in the engineering lab that you can put one of those rockets on the stand, and you can ignite it, and it'll give you a plot of time versus force. So to begin with, before you ignite it, there's no force pushing on the sensor, and then you ignite it, and the sensor recognizes the force, and it's not completely a perfectly straight line, and then you have maybe a peak in it. So since the force is not one constant force, in order to make a prediction of how high the rocket goes based on its force, we want to find out what the average force is. So what we can do is we can find the area underneath this curve, and it turns out that the software that collects that data for us will give us that area. And the average value, what we mean by that is essentially how tall of a rectangle would it take that's the same width as our interval from here to here. How tall will a rectangle need to be so that the area of the rectangle is exactly the same as the area underneath that curve? So our rectangle might have a height like that. So if we were to calculate the area of that rectangle, it would be the same as that blue region. So the area of the blue region is given by the integral, and let's change colors so maybe we can keep this straight. So for the blue region, if we had a function for that curve that gave us the force, we would integrate that function. Our variable in this case would actually be time instead of x. So our width would be dt, and we would go from A to B. And there's an equivalent area that, or an equivalent rectangle, that the width is given by B minus A, and there's some y value, we can just call it f average, such that when we multiply that height times that width, it's the same as the area of that underneath the force function. To get f average, so what am I calling f average? It's that height. Just divide both sides by b minus a. B and A are constants. That's our interval. So that's how you get the average force. It's 1 over the width of the interval times the sum of our function from one side to the other. So they give us a problem in the book that says find the average value of some function. And they give us a function like 8 minus 3x perhaps on the interval that goes from 0 to 2. So if we want to find the average value of that function on that interval, we do 1 minus b over a times the integral of 8 minus 3x dx from 0 to 2. So that's going to be 1/2 times, when we integrate that function, when we integrate the constant, we pick up a variable. 3 is a coefficient, and when we integrate x to the first, we make our exponent 1 bigger, and we divide by that exponent, and then we evaluate that from 0 to 2. So to evaluate that from 0 to 2, we put a 2 in, so 8 times 2 minus 3/2 times 2 squared, and then we plug a 0 in, and when we plug a 0 in, we get 0 minus 0, so that's gone. So we have 1/2 times 16 minus, we can cancel this 2 out with one of these 2's, so that leaves us 3 times 2. So we have 1/2 times 10, or 5. So the average value of our function on the interval from 0 to 2 is 5. Sometimes the function will be above 5, sometimes it'll be below 5, but in our interval, that's how big the function is on average. Let's just sketch that real quickly. So that function's extent minus 3x from 0 to 2. If we put a 0 in, our height is 8. If we put a 2 in, 3 times 2 is 6. 8 minus 6 is 2. So this is our region. So we got 5 was our average value. Half of the time, our function is above 5. Half the time, our function is below 5. And notice this is symmetric. This and that are equal in sizes, so it makes it easier to see that, yes, 5 is the average value there. Another way to think about it is that if you could break this into individual values instead of a straight line, a constant line, if we added up every y value along that line and then divided by how many y values that was, this number is the average of those y values.